fundamental issue here in regeneration is that the material is completely gone. So no other healing approach can be useful in that case. We have to regenerate the host material anew. Historically, when you look at self-healing materials, the largest scale at which you would see a healing event would be something on the order of maybe 100 microns. And that's a very small dimension. It's something on the order of the width of a human hair. In the kinds of experiments that we've done now, we've been able to regenerate impact damage that exceeds, say, 35 to 40 millimeters in size scale. So that's something about like that compared to a single human hair. So it's really expanded by orders of magnitude the size scale at which you can see the regrowth and regenerated process happen. One of the problems that we faced in embarking on this whole concept of regeneration is gravity. And the problem here is that the fluids that you want to deliver to the site of damage are being acted upon by gravity. And at some critical size scale, gravity overwhelms any forces that are inherent to that fluid, namely surface tension. So when that happens, the gravity will force that fluid to flow out, and you'll have essentially a bleed out event. So we had to overcome that, and the way we overcome that is to develop a chemical system that has a gelation that happens very quickly, like akin to blood clotting in humans and other biological systems. So it gels very quickly and is retained in place, even under the influence of gravity. Simultaneously, going on in the background in the same material mix is a polymerization reaction, but that extends over a much longer time frame, maybe on the order of several hours. So the material gels and is retained in place, and simultaneously coming along behind it, the material polymerizes, and it achieves a very hard, strong, structural polymer consistency at the end of that process. What we had to do is to isolate the critical components that trigger those reactions into two separate solutions. Otherwise, if they come together, all the reaction begins immediately, and you would see complete clogging of the vascular bed. So they're isolated in two separate fluid streams. And then when the damage occurs, those two fluid streams come together, and that starts the clock of the reaction. So as we pump these chemicals into this damage region in which a gel is starting to form, one might naturally think that you can't pump into that hole anymore, but in fact you can. The gel is not a structural material yet. It's still quite soft, and so a little bit of pressure allows you to continue to pump in the fluids that are necessary to regenerate the entire hole. So in previous work in our group, we have actually developed the techniques to make vascular material systems. And we do that through a variety of techniques, but in the end, what you end up with is a material that has a network of microchannels that are interconnected, possibly in all three dimensions within that host material. And we've developed techniques such that you can vascularize it without sacrificing some of the inherent mechanical integrity and mechanical properties of that material system. In the end, if you were not aware of where damage would occur in a material system, you would need microchannel networks distributed throughout the entire volume of that material system. And so ultimately, you would see a vascular material that had a circulatory network containing the regenerative chemicals inherent for this reaction to take place. And one can envision an application here as it develops further where you would have a reservoir that's in the material system somewhere where it's maybe not stressed very much. And a slight pressurization of that network would allow you to release the fluids into these regions where damage had occurred, either a puncture event or an impact event or something like that. Gelation really dictates the structural appearance, the shape of that material that we're actually regenerating. So you can't retain a full three-dimensional shape that was there to begin with. It's still going to be dictated largely by gravity effects on the gel itself. But with continued work in regeneration and perhaps more sophisticated approaches, you could envision really getting at the heart of directed growth, where you sort of dictate how these materials form and the ultimate shape that they take after release and regeneration. In our initial work that we've published here, the chemical reagents that are used for regeneration are distinctly different than the substrate material that we put them into. But there's no reason why one couldn't envision having the exact same chemistry at play here, both in regeneration and in the host material that you're using. And when you do that, I think then you truly have a material system that is regenerative, because it's replacing the exact material that it was made from.